Okay, this is problem number 37 on page 41, chapter 2, kinematics. The problem reads, a ball player catches a ball 3 seconds after throwing it vertically upward. There are two parts to the question: with what speed did he throw it, and at what height did it reach? There are two ways to approach the problem, and it's important for you to recognize that there's some symmetry here. So I'm going to make a quick sketch on the side. We should recognize that the ball is going to go up into the air and then fall back down. There's a couple of important things to realize. The first one is that at the height, the maximum height that it reaches, we could say that the velocity is going to be equal to 0 meters per second. Its velocity is changing from positive or upwards velocity to a negative velocity vector direction at that point. We should also recognize here, equally importantly, that if the ball is thrown and caught at the same vertical position, we could say that y final and y initial are both equal to 0 or whatever we want to set that to, and therefore delta y is going to be equal to 0. So let's take a look at this first problem. I'm going to answer part B first, which is how high the ball reached. I'll start by using one of the equations of motion, but I want to write down what I know first. I know that the acceleration, of course, is going to be negative 9.8 meters per second, and we know that the final velocity in this case will be 0 meters per second. Its initial velocity is unknown, and we know that the time, due to this symmetry, is going to be equal to 1.5 seconds. Note that the total time, which I'll write off here to the side, is 3 seconds. But you can recognize that due to symmetry here, that half the time, or the time to reach its maximum height up here at this position, is going to be half of that, or 1.5 seconds. All right, so we've got some things here that we can use. I can say, all right, well, v final is equal to v initial plus acceleration times time, and I should recognize that my v initial can be solved for. I'm going to say that v final minus acceleration times time is going to be equal to v initial, and therefore 0 minus negative 9.8 meters per second times my time of 1.5 seconds is going to yield my initial velocity. Running that through my calculator, I should get about 14.7 meters per second is equal to my velocity. My pen is behaving badly here. Meters per second is going to be equal to my initial velocity. Truncating for significance, I would call that 15 meters per second. So that's one approach to solving, strike that, that's actually the part A, the first question. How fast was the ball initially launched? Another way you could have solved part A to the first question would be to basically acknowledge that the total time of flight is equal to 3 seconds and analyze the entire motion here. This then, delta y being 0, becoming critical. Instead of setting up using the second equation of motion, we'll use the first one, the one originally developed by Galileo in the inclined plane. I'm going to use y final equals y initial plus v naught t plus 1/2 at squared. I can subtract y initial, or my initial position, from both sides. That equation becomes delta y is equal to VOT plus 1/2 at squared. I should recognize that my delta y is equal to 0. That allows me to drop that term right off, and now I can solve for initial velocity. It's going to be 1/2 at squared negative, right? I've brought this term here over to the left-hand side of the equation, and I get is equal to v naught t. Dividing both sides by t, I get negative 1/2 at is equal to v naught. Plugging these numbers in, I get negative 1/2, negative 9.8 meters per second, and that is going to be, times the full 3 seconds is equal to v naught. Plugging these numbers into my calculator, I get really the same thing. 1/2 of 3 is 1.5, and I end up multiplying that by 9.8. Notice that the negative signs here are going to cancel out, the negative here and the negative here, and I end up getting the same thing. 14.7 meters per second is equal to my initial velocity. Dealing with my significance, I'll round that to 15 meters per second. So there are two separate ways of approaching the first question, which was how fast was the ball fired. There are two approaches to answering part B. Part B asks how high did it go, and you should recognize that you're trying to solve for delta y, or our vertical displacement in this particular question. We know the initial velocity. The initial velocity is 14.7 meters per second, and we know that it's in the air for 3 seconds, and of course we know the acceleration is equal to negative 9.8 meters per second squared. You have a lot of information here, so you can approach the problem using a couple of different routes. The first one would be you could use your calculated initial velocity from part A and use the third equation of motion, Vf squared equals Vo squared plus 2a delta y. Everything here is known. We know Vf, Vo here again at h max, or our maximum height, is equal to 0. And we know the acceleration, and we'd be solving for delta y. If we chose to move forward with that equation, we get Vf squared minus Vo squared divided by 2a is equal to delta y. Plugging some numbers in, I get 0 squared minus 14.7 meters per second, and that entire term is squared. Dividing it by 2 times negative 9.8 meters per second is equal to our delta y. Running those numbers through my calculator, you should get somewhere on the order of 11 meters being our vertical displacement in part B of the problem. There's another way to solve this. You could, with the given information now, elect to choose the first equation, which is going to be y final equals y initial plus VOT plus 1/2 AT squared. We could, now that we know VO, solve for delta y and use the first equation of motion. Let's go ahead and do that, and then we'll be done. Rearranging the equation, I'm going to get delta y on the left is equal to VOT plus 1/2 AT squared. And now I've got everything that I need. I can say, all right, well, my vertical displacement is going to be equal to my initial velocity, which is going to be positive 14.7 meters per second. Of course, that's an upward velocity, times the time. Notice I need to make this adjustment to 1.5 seconds because we're talking about half the time that it takes to get up here to its maximum height. And to that, I'm going to add 1/2 times negative 9.8 meters per second times 1.5 seconds squared. Notice that the first term here is positive, and that the second term here is negative. So I'm going to get two numbers, the second term being subtracted from the first. When I run that through my calculator, I should get something similar. And the answer to this problem is still 11 meters.